Well, we come to the conclusion. Let's rephrase the question. We want to find a point on the g of xy curve where motion along that curve results in a maximum of your f function. Think again, maybe a maximum of your temperature function, or a minimum of that function. So you're confined to this curve. That's called your constraint. G of xy equals 0 is your constraint. So the g equals 0 curve confines you, but there's a temperature function throughout the plane. So that temperature function at every point, not just points on the curve, that temperature function has derivatives everywhere in the plane, or everywhere at least in the part of the plane where the temperature function is continuous, is valid, etc. Okay? So what does it look like if at this point there's no change? We saw that if it looks like this, there's a change because the temperature is increasing in this direction. It has to be increasing in this direction, which means that it's decreasing in the direction of your unit tangent as you move along the curve. Okay, well here, the rate of change of xy with respect to movement along g is 0 whenever the picture looks like this. Whenever your gradient, which is your direction of maximum increase, has no component in the direction of t. Okay, we have 0 rate of change if and only if this is a right angle, because this vector has no component in the direction of t. There's therefore no rate of change in the direction of t. Now, this just comes back to the simpler statement I made here, but we wanted to see why it's true, that the direction of maximum increase is perpendicular to the direction of no change. Now here we talked about it in terms of just the function g, stating that this is your direction of no change, this is a direction of maximum change in the function g. And remember, g is also defined through the whole plane, so we can talk about its gradient in this direction. We're confining ourselves to this curve, but that doesn't confine the g function to the curve. The g function certainly has a rate of change if you move in this direction. Now, it's most relevant to the f function at this point. Same thing can be said. In any direction perpendicular to your unit tangent, that's going to be the direction of maximum rate of change of whatever it is that's changing. Okay, well, I say this can only be so if del f has 0 component in the direction of your unit tangent vector. That is, if del f is perpendicular to your unit tangent vector. Okay? Now, where does that leave us? If we put all this together, how can we test whether the function f of xy has a maximum at a point on the constraint curve, on the level curve of g of xy? Think of this picture. Think how this picture differs. How would the picture look if we included all the behavior of g? So you should think about that for a minute, and I'll come back in another video and we'll answer that question.